So I will introduce you what is the first Maxwell equation. The first Maxwell equations are in the form of Gauss law, which stated that electric flux through a closed surface is equal to the charge enclosed by the surface. The formula given are here and here. To apply Gauss law, first we need to find the symmetrical axis. Once we found the symmetrical axis, we can construct a mathematically closed surface. Formula given are Q equal to psi, which is we know Q is the total charge enclosed while psi is the electric flux. Q can be derived as integrate rho v dv and psi can be integrated into the d dot ds. Rho is the volume charge density while d is the electric flux density. Thank you.
Hello, Professor Chua here. So, as we know, I want to present about Maxwell equation. So, Maxwell equation has 4 equations. I want to talk about equation 2, which is a gas law for magnetism. Gas law for magnetism says that magnetism monopole does not exist. It's really more a statement that something we might use to derive expression. So, as we know, charge exists as a positive or negative. But in magnetism, whenever you have a south pole, you also have a north pole. There are no single or monopole as yet discovered. So, for example, the application of Maxwell equation here, Gauss law in magnetism, which is if you have one magnet and equal. So, let me see for the next application and next equation. Okay, bye.
Magnetic sources are always dipoles with a north and south pole, and magnetic field lines that leave from the north pole and return back to the south. When you're looking at how a magnetic field interacts with the surrounding surface, you see that the field lines that leave the surface out of the north pole must enter back through the surface to reach the south pole. This results in the overall magnetic flux being zero. If you compare this with Maxwell's first equation, you can tell that the format, with the integral of the magnetic field over the surface area, is the same, but
so we will continue to the third equation of Maxwell equation, which is Faraday's law. What is Faraday's law? Faraday's law discovered that the induced EMF, which is VEMF, in any closed circuit is equal to the magnetic flux by the circuit. It means that the equation given is VEMF is equal to negative N d flux over dt. So in a single circuit, the N we will assume is 1. So the equation is VEMF equal to negative dV over dt. So when we use the Stokes theorem, that is why we get the Faraday's law equation. The originality of Faraday's law, which is del cross E is equal to negative dB over dt. So, in this equation, we can see that the electric field term and magnetic field term are in this same equation. Also, the time derivation also here. So, in this equation also show us that the time varying electric field is not conservative. It means that the del cross E is not equal to 0. It equal to negative dB over dt. So it has relation which is this is B and this is E. So when any change of magnetic field, which is B, will create voltage. Will create voltage to be induced in the coil. So when in a coil, when there is a change of B, whether it increase or decrease, so it will produce voltage induced in coil. So I will explain you about the application of the Faraday's law in this Maxwell equation.
Hi, I will talk about the fourth Maxwell equation, which is the Ampere's law. Ampere's law equation given which is this one. Then cross H equal to del D, which is the electric flux density over the del time, plus which the electric current, which is J. So how to apply that equation? So use a stroke theorem. When looking at the Faraday's law, we can write an Ampere's law, which is this one. So on the right side equality of the equation, we use the stroke theorem to change a line integral around the closed loop into a curl of the same field through a surface enclosed by the loop, which is S. So we can write the total current I as a surface integral of the current density J, which is this one. Then from the two equations that I mentioned before, we can substitute them together and get a new form for Ampere's law, which is this one. We have a new form of Ampere's law, which is the curl of the magnetic field is equal to the electric current density. We will look about the divergence of the Ampere's law as written as this. Then we know that the divergence of J is always 0. Maxwell proved that the divergence of J is not 0. And Maxwell knew that the electric field and the electric flux density was changing within the capacitor. And that he called this term the displacement current density, which is this equation. From the equation, we can combine and rewrite the final form of the Ampere's law.